We're going to move on to solving nonlinear systems of equations. However, not much is going to really change from our skill set. We're still going to be using substitution, we're still going to be using elimination. So if you've really gotten comfortable with those two methods, this is going to be pretty much a breeze. The only thing we're doing now is because we have nonlinear systems, we can have more than one equation. So let's just jump right into it. Let's solve the following system. Let's take y is equal to x squared minus 4 and y is equal to x plus 2. I want to solve this system of equations. Just like with our linear system, we have the option between substitution and elimination. I think a good case could be made for either in this problem. You could use substitution very easily by replacing one of the y with the other, basically just setting the two equations equal to one another. Or you could eliminate the y's pretty easily by subtracting the two equations. I'm going to use substitution. I think that'll be a little bit easier. So I'm going to take my x squared minus 4, plug it in for my y. So these two equations are equal to one another. I need to get everything to one side of the equation because we do have a quadratic at this point. So this is where it becomes a little different than the linears. Linears we would isolate the x, but here because we have an x squared, we just have to solve these using our skills of solving equations. We have a quadratic, we need to get everything to one side. Let's subtract that 2 over as well. So now I need to solve this, and I can do that by factoring. X, 6 is a minus 3 and a plus 2. That will give me the negative 1 there. So I get x is equal to 3 and x is equal to negative 2. Before we were only getting a single point. Now we are having two values of x that will solve this, and we'll talk about why that is in just a second. I need to take these values. I still need to get the y's, so I'm going to plug in. I have options here. I could plug into the first equation or the second equation. I'm going to choose the one that looks easier, and that definitely is the linear. So I'm going to take my 3, plug it into the x plus 2, and I'll do the same thing with my negative 2. So when I plug in the 3, 3 plus 2 is equal to 5. Plug in the negative 2 plus 2 is 0. So I get two solutions, 3, 5, and negative 2, 0. There is my solution set, two different solutions. So why is it that we are ending up with two solutions? Well, think about it. We know what these shapes are. We have a quadratic on the top. We have a linear underneath. Quadratic's been shifted down by 4, just ballparking, that would be it. The linear has a y-intercept of 2 and a slope of 1. Notice how many times did those two equations come into agreement with one another? How many times did they touch? Two different places. So I did this one actually a little bit opposite of what I would typically recommend. I typically recommend starting with the picture. Think about the picture first to think about how many solutions you will have. That is valuable for a couple reasons. It's always a good idea to know where you're going with something. It's a good idea to know how many solutions you're looking for, so that way if you get one, you don't just stop and say, oh, I'm done. You make sure you progress on to find however many you would expect to have. But two, there will be times that if you were to take your numbers and plug them in to not necessarily the wrong equation, but the harder way to do it, or the equation that's a little bit more forgiving, you can end up with too many solutions. And so we'll see an example of that in just a second. But we want to avoid having too many solutions by plugging into the more restrictive equation, but also thinking about how many solutions we should have to make sure that we didn't end up with too many solutions. So let's take another example. Let's take x minus 1 squared plus y squared equals 4. And x plus y equals 1. So the top equation we should recognize is a circle. The bottom equation is a line. So if we think about a circle and a line, we know the circle shifted to the right by 1, and it has a radius of 2, so ballparking that would be what it looks like. The line, move the x over, we'd have a y-intercept of 1, a slope of negative 1. It would be looking something like this, but if we think about crossing a circle and a line, at most there are two solutions. I say at most. Is it possible to have less? Yes, and that was true with the quadratic as well. We think about a circle, let me not even put onto an axis. If I have a circle and a line, it is completely possible that they don't actually cross. And if I think about a circle and a line, it is possible that the line skims the circle, meaning we have one unique solution, but it doesn't actually cross through it, only it brushes it. We have that one solution, we don't have more. Now, based on our drawing, that's not what we see here, right? We drew these pretty well to scale. We should see two different solutions. However, I do want to point out that it is possible that they still won't touch, or that they do have that one solution. We should recognize these when we're solving the system, though. If we see something like this, that is going to occur with a multiplicity on the x or the y. The same way we saw that with multiplicities when we're finding roots back in chapter 2, if we had a multiplicity of 2 or 3, that a function could touch and turn, or it could skim the x-axis. We can skim other functions. With this one, now that we're not dealing with strictly lines, now that we're dealing with x squared functions and y squared functions, it is possible to incorporate imaginary solutions. So we should be able to tell that we're not going to have a real solution. It does mean that they won't cross, but it doesn't mean there's no solution to it. It might be imaginary. Same thing was true up here with the quadratic. It is completely possible for a quadratic and a line not to touch, or it is possible that they skim off of one another. So we should have expected at most two solutions. We should expect at most two solutions here. It does not prevent less. Once we draw out the picture with a little bit more accuracy, we should predict it a little bit better. We know that on this one we should have two solutions, but we are saying essentially two or less. Okay. Let's solve this one using, I think substitution definitely a lot easier on this one than elimination. So I'm going to solve for the easier variable. X or y equally easy here, but I'm going to solve for the y because I think that looks a little bit easier to plug into. Y equals 1 minus x. So let's plug in x minus 1 squared plus 1 minus y squared equals 4. Try that again. 1 minus x squared is going in for the y. This should be an x. My eraser's not working. So 1 minus x squared. And so now let's square these things out. So we'll have x squared minus 2x plus 2. Remember, we have to not just stick the square on both terms, but we have to square that whole expression, meaning FOIL it out. Then here we'll have, try that one more time too. I'm making a few errors here. Gotta be careful. This should not be a 2. This should be a 1. So again, my eraser, sorry, has stopped working here. This needs to be a 1. And then on the second one, we square out this, we get a 1 here. My tablet is frozen, there we go. A 1 on the first thing. Multiply the 1 and the x and double it, we get negative 2x, and then we multiply the x by itself, we get an x squared equals the 4. Again, I apologize, these are just 1s. So now I'm going to simplify. We have an x squared and an x squared, that is a 2x squared. We have a negative 2x and a negative 2x, that is a negative 4x. We have 1 and 1 will give me 2. That's equal to a 4. I have a quadratic, so I need to get everything to one side. So we'll have a 2x squared minus 4x minus 2 is equal to 0. I can factor off that 2. So once again, my tablet has frozen. And I would be left with an x squared minus 2x minus 1 equals 0. Now, this one is a little bit more challenging to have to factor. It doesn't factor. So if I can't factor, what can I always do? I can use my quadratic formula. Let's take the inside of the parentheses and let's apply our quadratic formula. So we'd have negative 2, which is positive 2, plus minus, square root of, then we're going to take our b and square it. So we get a 4 minus 4 times our a times our c, all over 2 times the a. So we get a 4 plus 4, which is 8 over 2. And then the square root of 8 is 2 square roots of 2. So we can simplify everything here by a factor of 2, and so we get x to be 1 plus or minus root 2. So there's our x. This one is not a pretty number, it's irrational, but it's not really that ugly either. By using our our algebra, we were able to get those exact solutions. This is one place that I referred to in my earlier video on just solving system equations. We can do these things graphically, but we won't necessarily end up with exact values. This will always get us to these exact values. So we get 1 plus minus square root of 2, meaning we have two different x's. Now, coming all the way back up here to the top where we started, we had the circle, we had the line. This is an example where it really does matter which one we plug into. If we think about why that is true, if I plug in this x, right, 1 plus the square root of 2, that would be approximately 2 and a little bit. If we look at the circle, there are two places that would be true on that circle. Here and here, both of those values would solve the circle. Only one of them solves the line. Same thing on the negative side. We have the negative point something or other here and here. Only one of them works on the line. So I want to make sure that I'm plugging into the more restrictive function, which is the line. I'm going to take the y equals 1 minus x and use that to solve for my x's. Sorry, solve for my y's. So we know we have an x of 1 plus the square root of 2. And we have an x of 1 minus the square root of 2. If I plug those in, I have y equals 1 minus 1 plus the square root of 2. And then y equals 1 minus the 1 minus the square root of 2. I do need to remember to distribute that negative, so our y would be equal to 1 minus root 2. And that would give us just a negative root 2. On the second one, we'd have 1 minus a negative turns into a plus root 2. And so when we simplify those, we get root 2. So in my solution set, I have an x value of 1 plus root 2, comma negative root 2. And I have a 1 minus root 2, comma positive root 2. And there are my two solutions, as we'd expect. A couple things I want to stress here that I see mistakes made. Don't leave the plus and minus when you go to plug in, because a lot of times I'll see students, they'll just write a plus minus on the x, and what that means is you'll get a plus minus on the root 2. If I say my solution set is 1 plus minus root 2, and then plus minus root 2, just finally switched over to red, which is what I wanted a second ago. If I leave that plus minus on there, we're going to end up with actually 4 solutions, because what this is saying is I could have 1 plus root 2 and the positive root 2, which is not a solution. I could have 1 minus root 2, a positive root 2, which was the solution. I could have 1 minus root 2 and negative 2. That is not a solution. So don't leave it with the plus minuses once you go to solve. Once we have those plus minuses, there are two unique solutions. So we need to treat them as those two unique solutions. We need to have the positive case and the negative case so that we can have those unique y's with them. They are unique y's. So that is one thing to be careful of. And the second thing to be careful of, like I was saying earlier, we want to plug into the more restrictive equation. So if I'd plugged into this first equation, if I plugged those x values into that line, the circle instead of the line, I'm going to end up actually with two different y's for each x, because the circle is predicting all 4 of these positions. The line only has the 2 correct positions. So always be very careful of that. Let's take one last example. Here we have the equation y squared plus 2x equals 3 and negative x plus y equals negative 5. We should recognize that bottom one as a line, but the top one is potentially a little bit different. You may not have seen that in the past. Some of you may have. But if we think about an x squared, we know that is a quadratic, it's a parabola facing up. Y squared, that is a parabola facing sideways. So looks like that. So we have a line and we have a parabola. There are going to be some equations in this section that we have not studied before in terms of their shapes. There will be some ellipses and hyperbolas. If we see these x squareds or y squareds, they should be lending us to believe that we have some odd shapes. So if we think about crossing these over, it is possible to have more than one solution. We can't rule that out. We should be looking for those multiple solutions. But just like we saw in that last circle, we should always, once we find that first variable, we should always plug into the more restrictive equation, the line. So because we're not sure exactly how to graph this one from the start, I'm just going to jump right into the math. I do think that substitution would be easier on this one, although I haven't done elimination yet, so let me do elimination on one just to show it. If I'm going to eliminate anything here, it's going to have to be the x's. The y's aren't going to eliminate. We have a y squared and a y. So I'm going to multiply the second equation by 2 so that I can get the x's to match. So we'd have the y squared plus 2x equals 3, that stays the same. Then I'd have a 2y minus 2x equals a negative 10. I just reordered those so the x's are sitting on top of one another. And now I can just add those two equations to each other to get the x's to cancel. So we'd have y squared plus 2y. Those are not like terms, so I can't cancel those out, or I can't combine those in any way. The two x's do cancel. 3 minus 10 is a negative 7. So we have the equation y squared plus 2y minus, plus 7 equals 0 once we set it equal to 0. And we'd look at this for a second and we'd say, oh, it doesn't factor, which means I need to use my quadratic formula. So I'd have a negative 2 plus or minus square root 4 minus 4 times my 1 times my 7 all over 2 times my 1. Negative 2 plus or minus 4 minus 28 is a negative 24 over 2. That's interesting. We've just ended up with a negative inside of our square root. And that tells us we're ending up with an imaginary solution. We can pull that I out. Now with lines, remember, if they didn't cross, there's no way for us to solve that. We can't bring those imaginary solutions into lines. Two parallel lines will never touch, not in any theory, not in any context. However, the same way we talked about quadratics, not crossing the x-axis, but still having solutions, just being imaginary solutions, we can talk about systems of equations not crossing. So this one I think is actually left if I remember correctly. Not crossing, yet we can still solve it because there are imaginary solutions that would solve something like this. So I'm going to continue in this problem. I'm not going to just say it's inconsistent. That is not true. There are imaginary solutions, but I can still find those solutions, no real solutions. So I can pull a 2 out of that. I'd have the 6 still on the inside. 4 times 6 is 24. Square root of 4 is 2. I can simplify everything by a factor of 2, so we'd have negative 1 plus minus I root 6. So we've ended up with two different x values. X is equal to negative 1 plus root 6i and negative 1 minus root 6i are my two x values. I have two x's. I now need to go and get the y's associated with those. I have two equations. I'm going to plug into the more restrictive equation, being the linear equation. And I think to solve for y, it'd be easiest just to go and solve for y here too. So I'm going to add that x over to the other side. Y is equal to x minus 5. So we're going to take our y, we're going to plug in our x, negative 1, plus the square root of 6i minus 5. And so we get a negative 6 minus root 6i. Then we're going to do the same thing, but for the I with the negative in between, we'd have negative 1 minus root 6i minus 5. And so we get negative 6 minus root 6i. Did I do wrong there? I needed, that should have been a plus. They can't be the same, right? We start with two different things. That was a positive root 6, and I just, for no reason, I'd all switched it over to a negative. So it should stay a positive root 6i on the first solution, a negative root 6i on the second solution. So now we have our solution set. The x that solves it, negative 1 plus root 6i, if we use a y value of negative 6 plus root 6i. And then the other solution that works is the negative 1 minus root 6i, with a y value of negative 6 minus root 6i. So we're using the same skills that we did for the linear systems. We have substitution, we have elimination. The only difference is we are now allowed to have more than one solution. We're now allowed to have imaginary solutions. We can see any number of shapes crossed. So we've been working a lot with lines, but we could have a parabola crossed with a circle. We could have some sort of oval ellipse shape crossed with a circle, a line, a parabola. We could have a square root function. We could have a cubic function. So practice quite a few of these because we want to get practice at being able to handle any function that we come across. But the key is substitute or eliminate variables. Once you get rid of that second variable, once you're down to just one, then you're taking it and you're solving it the same way you've solved any other equation.